So we're going to revisit a concept that we did in two dimensions, and that is the dot product. Okay, so today we're just going to look at what we can do in three dimensions. Okay, everything is set up identical to the way it was in two space, so we don't have to redo or refigure out what it is. Since we looked at it geometrically in two space, it's the same thing. It's the same concept in three space. Okay. So the dot product, if we take a look at, again, what the dot product is geometrically, by definition, all right, we multiply the magnitudes together with the cos of the angle between them. And we know that the tails are lined up when we do the angle between vectors. Okay. Algebraically, the dot product, we have basically the sum of the product of the corresponding components. All right, so that's the same. So we take a look at this first example here. We've got example vector u, vector v is given. We want to find what the dot product is and the angle between them. And remember, the angle between them is really the thing that we're looking at using the dot product a lot, because we can find the angle once we know what the dot product is itself. So taking a look at the dot product in A. All right, let's just switch your color back to black. And we have the dot product between these two vectors would then be -8 times -2, which is 16, plus 3 times 7, 21, plus 5 times 3 is 15. So we've got the 31 and 21, 52. So there's our dot product right there, the 52. Okay. The angle, right? We are going to use the combination of the dot product, the definition, all right, because it's got the angle in it. We can figure out what the magnitudes are, and we already figured out what the dot product is. Okay, so let's take a look at this one. Call that B. We have cos theta is equal to the dot product divided by the product of the magnitudes. So the dot product we know is 52. The magnitude of vector V, we can do that, the square root. So we have 64 plus 9, that would be 73, plus 25 would be 98. And then the magnitude for vector V, 4 forward 49 is 53, 53 and 9 would be 62. So we have the cosine theta. All right. If we look at the inverse of this, 52 over the square root of 98 divided by the square root of 62. Okay. Let's take a look at what that is. We have the cos inverse, 52 divided by square root of 98 times the square root of 62. Make sure I got enough brackets in there. And it looks like the angle is approximately 58.2 degrees. Okay, so that is basically straightforward if we did all of our algebra correctly. Okay, we have what our dot product is, and we can find the angle between the vectors. Okay, so that's one concept we've done in the past. We're just rehashing it with three dimensions now. Okay, so that's fine. What we can do with this is just a quick little example. You've got a triangle, you know the vertices, we've done this in the past. You then would be able to figure out the angle A here. And I do want to go through this one and point out a couple things with this one. So if you've got your A, B, and C, and you're trying to find the angle A, let's just draw it out. Okay, and we'll just assume that A, B, and C look like this right here. Here's what we have to remember. If we are looking for angle A, which we are here, that means to use the dot product, we have to set up our vectors to be tail to tail in that case. So we are specifically looking for vector AB, right? And vector AC. Okay, we got to make sure that we're going tail to tail in order to use this process using the dot product and all the rest of it. Okay, so let's take a look. I've already got the answer down here, but let's take a quick look and see how we find that answer, right? Again, let's figure out what is AB, right? Vector AB is OB minus OA. We use the vector notation in this one, right? Because it goes from the head of the second to the head of the first. Okay. So OB, OA, you've got -1, take away 2 is -3, -4, take away 3 is -1, and 5 take away 4 is 1. AC is OC minus OA. And so we have 3 take away 2 is 1, 4 take away -3 is 7, and 2 take away 4 is -2. Okay, so this is the key thing here to make sure that they are lined up tail to tail. This is how you do it, right? It's if you're looking for angle A, it's AB and AC vectors that you're looking for. Okay, the rest is just finding it the same way as we did above, right? Using the dot product, using the magnitudes of these, all right? And you can verify that that's what you have, all right? So next concept, the projection of A onto B, right? We symbolize it this way. Again, we did this, we formulated it using geometric vectors in 2-space. It's the same concept in 3-space. We don't have to redo what the projection is. Okay, we know that looking at the projection of A onto B or a vector onto another one is using the dot products, right? So A onto B would be A dot B divided by B dot B times the vector B. Okay, so it's in the direction of B. You have to remember you're in the direction of B. All right, the second one. So what we'll do is take a look again. We've got two vectors. Find the projection, so which is a vector, finding the scalar projection, the magnitude of that vector. All right, we'll take a look at it. So again, A dot B, let's just go through that. We've got A dot B, so A projected onto B, A dot B. So that would be 3 plus 8 plus 7, right? That's you're doing the dot product. Now you're doing the dot product of B dot B, which is basically the magnitude squared 2, but B dot B, you've got 9 plus 4 plus 1, and then we multiply that by the vector B. Okay, so 15 and 3 is 18 over 14 times the vector itself, and we can go through that. You can even reduce that, right? 9 over 7 you can do, multiply by -3, 2, and 1, right? So we end up with -27 over 7, 18 over 7, and 9 over 7. Okay, so there's the vector, or the vector projection of A onto B. Magnitude, you know how to take the magnitude, right? Take the square root, the sum of the squares of each of the component. So you could do -27 or just 27 over 7 squared, all right, plus 18 over 7 squared, plus 9 over 7 squared. Okay, so I believe I've got the answer in here, right? When you work that through, This one's actually written incorrectly, and you can see that. We should have brackets around this squared. I'm not sure why they didn't show up in this one. Okay? But anyway, that's what you've got. Those are the old things that we have. These are not old things because we've done them in 2D and we're just converting to 3D. There's no difference except for the third component. Okay, so we're reviewing basically those concepts. The extension that we can do with the dot product in 3 dimensions is to find a normal to the plane. A normal is we're looking for a vector that is perpendicular to the plane itself. Okay, so let me just show you a little bit here. I've got some examples. All right, so the outside, we see this parallelogram, right? That's a plane. Okay, we've got normals. I've given you 4 different normals here. Okay, they are all perpendicular. They are of various lengths. Okay, they can be placed anywhere on the plane itself. All right, the vectors A and B that I have there, those are 2 non-collinear, non-zero vectors. All right, that define this plane. They're on the plane. What we are going to do with this is the extension, is we are going to come up with one of these vectors that are perpendicular to the plane itself. Okay? Now here's the idea. If a vector is perpendicular to the plane, it's perpendicular to every vector that's on the plane. Okay? So let's say, for example, we have this vector here. We'll call it n for normal, vector n. Okay? We know that n is perpendicular to vector b. Why? Because vector b is on the plane. We also know that n is perpendicular to vector a for the same reason. Okay? Now here's where the dot product comes into play. Since these are perpendicular, then if we take the dot product between the two of them, we're going to get an answer of 0. Right? N dot b is 0, n dot a is 0. Okay, we're going to use this fact in order to find out one of the n's, okay, that can fit anywhere on this plane. All right, so here's what we'll do. Let's just start off with, and this is our final example of the day, we're going to say given vector A, and we'll just use 1, -2, -3. B will be another, but a non-collinear vector. So B would be something like, we'll go 2, we'll say -4 and 1. Okay, we're going to determine vector n, and vector n is just going to be x, y, and z. Okay, such that n is perpendicular to both A and B. All right, that's what we're going to do. So here's how we do it. Again, since they're perpendicular to A and B, then we can say that n dot A is equal to 0 and n dot B is equal to 0. Okay, so n dot A, let's take a look at it. Remember, we're multiplying and adding the components together. So we've got an x minus 2y minus 3z equals 0. And in the second equation, we have 2x minus 4y plus z equals 0. All right, one equation, 2 equations, given the fact that n is perpendicular. All right, dot product must be 0. Okay, so move on. Here's the thing. We have 2 equations with 3 unknowns. 2 equations with 3 unknowns means there's an infinite number of solutions. Infinite number of solutions. Well, how are we supposed to get 1? How do we know that there's an infinite number again? we take a look at the diagram I have. If you're given a plane and you just want to find out a vector that is perpendicular to the whole plane, well, look, I've only drawn four of them. I've only drew out four of these perpendicular vectors. You can see I can place the vectors anywhere. There's an infinite number. So the math holds up. The algebra is telling us there's an infinite number of solutions. The diagram shows us an infinite number of solutions. So how do we solve this? Okay, what we do, the method is, we let one of these coordinates, the x, y, and z, or components, be any number we want. Once we choose a number, then we can come up with a specific solution to the other two. All right. So what I would suggest is you let one of these, the x, y, and z's, be equal to 1. Stay away from 0. Okay. I would let anything, whenever I get to choose a number, in these cases, I would choose 1. All right, so if x is equal to 1, then we have 1 minus 2y minus 3z equals 0, and we have 2 minus 4y plus z equals 0. Notice here we have two equations with two unknowns. We solve with substitution or elimination, right? Your choice. I think in this one what I'll do is I'll set this up with elimination. We've done substitution before. So let's take a look, and what I want to do in this one is I'm going to multiply the first equation by 2, and I'm going to leave the second equation alone. So 2 minus 4y minus 6z equals 0. 2 minus 4y plus z equals 0. In order to get rid of the y's, I've got to subtract. Okay, so adding down, we've got 2 minus 2 is 0. That's y is 0. It looks like 6 is going to end up, or z is going to end up with 0, minus 7z. Minus 7z, right? Equals to 0. Z equals 0 in this case. Okay? If z equals 0, you can just simply, sub your z into, let's say, equation 1. So we have 1 minus 2y minus 0 equals 0, 1 equals 2y, y equals a half. Okay, so therefore our n is equal to 1, a half, and 0. Okay, now if you don't like fractions, you can leave it like this. This is it, and we're going to check to make sure that it works out. If you don't like this, then you just use a scalar multiple of it. We can also say or. We can then use our scalar as 2, or not our scalar, our normal vector as 2, 1, and 0. Right? Notice the scalar multiple. It should also be a linear combination of the n. It's also perpendicular to a and b. Okay? So let's just prove, or check rather, that it is perpendicular. What is n dot a? Right? n210 dotted with a. I forget what I put down for a. It looks like 1, negative 2, negative 3. So 1, negative 2, negative 3. That equals 2 minus 2, which equals 0. So it's perpendicular to a. We can check that it's perpendicular to b as well. So we know it's perpendicular to the whole plane. What was that? 2, negative 4, and 1. So we have 2, negative 4, and 1. So we have 4, negative 1, or negative 4, 0, which is 0 itself. So we have it. Okay. Our n is perpendicular to the plane. That's what we were going to be proving anyway. Okay, so you take a look at the process. All right, again, we're using the fact that since n is perpendicular, okay, to the two vectors, then the dot product is 0. Okay, this is another way of thinking about perpendicular vectors. I remember way back in grade 9, I talked to most of you saying whenever you hear perpendicular, right, you should think negative reciprocals, right? When we talk about the slope, perpendicular, negative reciprocals, right? Well, here's the thing now in grade 12, all right, with our algebra, our calculus class, all right? In vector world, you think perpendicular, dot product is 0. Okay, perpendicular, dot product is 0. So that's what we're looking for here. Okay, that was another example there. So you can take a look at these here. All right, review the concepts. Good luck.